Continue our discussion of drawing Lewis structures, focusing on some compounds that break the rules. So we've been using the octet rule as kind of our guiding principle for drawing Lewis structures thus far, but not everything always obeys the octet rule. Some things will have a central atom with either an incomplete octet, meaning less than 8 electrons in its valence shell, or an expanded octet with more than 8 electrons. So today we're going to be looking at which elements tend to do this and sort of how we know when we're going to be following the octet rule, when we're not going to be following the octet rule. So one exception that we've already seen is hydrogen. Because the valence shell of hydrogen is the first shell, is the n=1, which only contains the 1s subshell, it's only capable of holding 2 valence electrons. So that means that hydrogen has a filled valence shell when it only has 1 bond attached to it, and it will never have any lone pairs. So another example of something with less than 8 valence electrons is boron. So you will notice as you draw more and more Lewis structures that each group or each family of elements has sort of typical bonding patterns that it engages with most commonly. And for most of the families, it's a bonding pattern that follows the octet rule. So most of the time, it doesn't really matter. I could tell you that, halogens always have 1 bond, or usually have 1 bond and 3 lone pairs, but you don't need to know that as long as you can figure out how to fill up its valence shell. That's what it's going to do. But boron's family is a little bit weird because it prefers to form only 3 bonds, which leaves it with only 6 valence electrons. So if we draw the structure for this molecule for BF3, boron is in group 3, so it will bring 3 electrons. Fluorine is in group 7, so each fluorine atom will bring 7, and there are 3 of them. So that means in total, our structure for BF3 should contain 24 electrons. So we choose our central atom as boron since it is unique and less electronegative. And we can arrange our peripheral atoms, our 3 fluorines, around that. Next, we fill up the valence shells of our fluorines with lone pairs. And that takes care of all 24 of our electrons. Now with this structure, if I had asked you to draw this yesterday, what I hope you all would have done is look at this and go, boron has an incomplete octet. I should create a double bond. And when you do that, you get a structure that looks perfectly valid and is perfectly valid, but it's not the best structure. It just so happens that this is less stable. So this structure is not as good because boron is a little weird and does not follow the octet rule the way that most elements do. So this is actually the best structure for BF3 because boron just doesn't follow the typical rules. So we can also go in the other direction and have elements with more than 8 valence electrons. Not all atoms are capable of this. So for hydrogen, we said that the maximum it could hold is 2 because it's in the first shell, which means that the s subshell is all that's available to it. There's no more space in the valence shell for electrons beyond 2. In period 2, we have the s subshell and the p subshell, which gives us a maximum of 8 electrons that we can hold. But after period 2 is where we start to get d orbitals available, that the n=3, or the third energy level, contains a d subshell as well, which means that after we have filled up our s and we've filled up our p, there are d orbitals available in the same shell. They're higher in energy, but they're there and they can be filled up if necessary. So what that means is that any element in the 3rd row and beyond, so period 3 through 7, or row 3 through 7 of our periodic table, is capable of having more than 8 valence electrons if needed when it's a central atom. Note that this is only for when your element is the central atom. Peripheral atoms will never have expanded octets, and they will almost always have exactly a filled shell of valence electrons. It's very rare that they're incomplete. But when necessary, when you have no place else to put your electrons, if your element is in periods 3 through 7, you can put more than 8 on your central atom and it's totally fine. There are some elements that break the octet rule really commonly. You'll see it on sulfur and on phosphorus a lot, are probably the most common elements that you encounter that violate the octet rule. So we're going to look at one example of how we draw a structure that violates the octet rule. So this is one where you'll see we sort of have no other choice but to do that. So for ICl3, iodine and chlorine are both in group 7. So they will each bring 7 electrons per atom to our structure here. So 3 times 7 is 21, plus another 7 is 28 electrons in total. So since iodine is unique, we'll put that in the middle and arrange our chlorine atoms around it. And then fill up our valence shells first, of our peripheral atoms first, sorry. So at this point, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have placed 24 electrons out of the 28 that we need. At this point is where we go to our central atom to place any electrons that we have left. So we put one lone pair, brings us to 26 electrons total, and at this point, all of our atoms have filled octets, but we still have 2 electrons left to place. So on our central atom, if we look and find iodine on the periodic table, we see that it's all the way down here in period 5, so it's totally capable of having an extra pair of electrons on it. It has d orbitals available to put those electrons in, so every pair of electrons needs someplace to go, but iodine has that d subshell available that's perfectly happy to accommodate those 2 extra electrons since there's nowhere else to put them. Note again that this only happens to the central atom, so we can't put those electrons on chlorine here. Chlorine is capable of having an expanded octet, but it's always going to go to the central atom preferentially. So we have no other option but to have an expanded octet, but since it's iodine, that's fine. So once you learn this, that we can break the rules sometimes, my students tend to forget that the rules exist. So not everything is capable of violating the octet rule. Anything in these first 2 rows has a really hard cap, that hydrogen and helium, but helium isn't involved in bonding usually, cannot have more than 2 electrons, period. That's all that's available in its valence shell. Anything in period 2 cannot have an expanded octet. It cannot hold more than 8 because the second shell only contains the S and the P, and you're done. So you can use this idea to start to understand why some compounds exist and others don't, even though they look very similar. So for instance, SF4 and OF4 both have 4 fluorine atoms bonded to a sulfur and an oxygen respectively, and sulfur and oxygen are in the same chemical family, so you would expect them to have similar chemistry, similar bonding patterns, and form very similar compounds. But it is true that SF4 exists and OF4 does not. So if we draw the structures for both of these, we'll be able to see why. So they're going to be very much analogous since they're very similar compounds. Sulfur is in group 6, oxygen is also in group 6, fluorine is in group 7, and we've got 4 of them, and same over here. So 7 times 4 is 28, plus 6 is 34. So we'll have 34 electrons in this structure, 34 electrons in this structure. So when we draw our structure, our sulfur is going to go in the middle over here. Our fluorine, or oxygen, sorry, is going to go in the middle over here with our fluorine atoms arranged around it. Again, remember the exact placement of your peripheral atoms doesn't matter at all. From here we can fill up our valence shells of our fluorines with 3 lone pairs each. And once we've done that, all of our atoms have filled octets. So everything here has a complete octet. Each of our fluorine atoms has 1 bond plus 3 lone pairs for a total of 8 electrons, and our central atoms are each involved in 4 bonds for a total of 8 electrons. So everything has filled valence shells here, but our structures only contain 32 electrons so far. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we're still missing 2 electrons. And now is where we turn to our central atom to place those last 2 electrons that remain. So if we draw this in both of our structures, our central atoms have an expanded octet. That's fine for sulfur. That's not fine for oxygen. If we look back to where these are on the periodic table, sulfur is down here in period 3, where we have d orbitals available. So this is all right to have an expanded octet. In fact, sulfur does it all the time. Oxygen, however, is in period 2. The valence shell for oxygen is the 2nd energy level, which only contains s and p orbitals. It only has space for 8 electrons. It cannot hold any more. So the reason why OF4 doesn't exist is that we can't do this. Oxygen can't have an expanded octet, so there's nowhere to put those electrons. So this compound, OF4, has insufficient space to contain all 34 valence electrons that it needs. So since we have nowhere to put those electrons, this compound can't exist as we have it written. For sulfur, however, that's fine. So sulfur can have an expanded octet. So that means that SF4 can exist because it's perfectly fine for sulfur to take those extra 2 electrons. Oxygen doesn't have any place to put them, so OF4 cannot exist.